Hey, 7th grade. I'm here to teach your next lesson. We're going to be doing Chapter 9, Lesson 7. This is the last lesson in Chapter 9. I, at first, was going to skip it, but I really think it's one that we should do. It's called Independent and Dependent Events. You're going to need pages 778 and 779 from your math book, a pencil, and a calculator. We won't use the calculator that much, maybe just to simplify some answers, maybe get a couple percentages. Okay, so really quick introduction. We're going to take everything that we've learned so far about sample space, about the fundamental counting principle, and then also just about probability in general, how likely an event is to happen in comparison to the number of possible outcomes. And we are going to look at compound events again. And we know that compound events are when you have two separate events happening. And we are going to look at how you can find the probability of two different events happening using multiplication, using the fundamental counting principle. And we're going to also talk about how the probability depends on whether one event is affected by the other, okay? And let me explain that to you what that means, okay? So let's start with independent events, okay? An independent event means that when you have compound events happening, the result or the outcome from one event has nothing to do with the other. One doesn't affect the other. So let me give you an example of that, okay? So here's my little number cube from an earlier lesson and a quarter, heads, tails, right? So let's just say that we wanted to find the probability of flipping that coin and getting heads and rolling a 1 or 6 on that number cube. I want to know the probability of both of those things happening, okay? Not one versus the other, but both of these things. What is the probability that I could flip that coin one time and get a heads and roll that number cube one time and get a 1 or 6? What is the probability that both of those events could happen together? Now, these are independent events because when I flip that coin, my results there are going to have nothing to do with me rolling that number cube and the results that occur from that, okay? So these are independent events. Think about what independent means. When something's independent, it does not rely on anything else. So one event does not rely on the other. So here is all you do. You start with the probability of the first event. So the probability of rolling a heads or flipping heads if you flip a coin is a 1 in 2 chance, right? 2 possible outcomes, one of them is heads. Then you take the probability of the second event. Now we know a number cube has 6 sides. A 1 and a 6 make up 2 of those 6 sides. So there's a 2 in 6 chance. If you wanted to go ahead and simplify that to 1/3, you could, okay? Then all we do is we multiply the probability of the first event times the probability of the second event. Now we can also cross cancel here like we learned to do earlier in the year if we want to go ahead and get to a simplified answer first. So we know 2 and 2 can be simplified by 2. 2 goes into 2 once, 2 goes into 2 once. And that's going to give us a 1 in 6 chance of those 2 different outcomes happening at the same time. We could use division to convert that to a percent and look at that probability as a percent as well. So these are independent events because one does not affect the outcome of the other. Now, let's talk about dependent events. You probably already figured out kind of what that means. A dependent event means that when you have more than one thing happening, or if you're repeating more than one trial of an event, more than one time, okay, the results from one event will directly affect the results from the next, okay? So what happens the second time is dependent on what happened the first time, okay? They are directly related. So I'm going to use an example from an earlier lesson. You guys remember my jacks. This came from the simulation lesson. and they had represented rain versus no rain, I think. So in here I have 5 different jacks. There are 3 silver and 2 gold. I want to know the probability of randomly choosing a silver the first time, and then if I reach in and grab another jack, assuming that we did not replace the first one, what would be the probability of choosing a silver one again? Okay, so in here, if I look at it, okay, right now there's a total of 5 jacks in there, and 3 of them are silver. So there's a 3 in 5 chance of me choosing a silver jack. Now, if we do choose a silver jack and we do not replace it back into that bowl, then the second time I go to choose, now there are only 4 jacks in the bowl. And 2 of the 4, or half of them, are silver. So now, because there's only 4 jacks in there, 2 of those 4 are still silver. We can multiply, we can't cross cancel here, to get our probability, and we get 6/20, which then we could simplify both 6 and 20 by 2 and get a 3 in 10 chance, or a 30% chance that we could reach in and pull silver and then pull silver again. These are dependent events because the results of my second try will depend on what happened on the first one. I'm going to have 1 less silver in there to choose from. So the number of outcomes, possibilities is less, and there's 1 less silver in there. So you have to think along those lines. Okay, so I'm going to get my book ready. Again, you guys need to have 778 and 779 ready. Grab your calculator. Like I said, we're not going to really be using it a lot, but we are going to have some fractions that we may want to simplify today when we do this, and we'll get right to it. See you in a minute. Okay, guys, we're back and we're ready to work, starting on page 778. Numbers 1 and 2 want us to find the probability of the events given. It says a penny is tossed and a number cube is rolled. Find each probability. So for number 1, we want to know the probability of tossing tails on the penny and rolling a 3 on the number cube. So this is similar to the example I did in the introduction of the video. These are independent events. The result of one has nothing to do with the other. So let's start with the probability of flipping tails, okay? The probability of flipping tails is 1 in 2. The probability of rolling a 3 on the number cube is 1 in 6 because there's 6 different numbers, only one of them is a 3. I can use multiplication to multiply the probability of each. And remember, when you multiply fractions, it's top to top, bottom to bottom. So that's going to give us a 1 in 12 chance. That is already simplified. So that would be our final probability. Now we know that we could also convert this to a percentage. I'm going to skip that step today because hopefully at this point you guys are feeling pretty confident about how to do that. Number 2, what is the probability of flipping heads and then getting an odd number on the number cube? Okay, so again, there's a 1 in 2 chance of tossing heads on the coin. And because there is a 1, 2, 3, 4, 5, and 6 on the number cube, we know that 1, 3, and 5, or 3 of those 6, or you could even immediately write that as half, would be odd. And then we can multiply. 1 times 3 is 3. 2 times 6 is 12. And we want to always simplify our answer. We know that we can divide both 3 and 12 by 3 to get to 1/4. So a 1 in 4 chance, which you should be connecting to a 25% chance of tossing heads and then rolling an odd number. So these were independent events because one had nothing to do with the other. Number 3 gives us an example of dependent events where the first event does directly affect the second. It says that we have cards that are labeled 5, 6, 7, 8, and 9 in a stack. A card is drawn and then it's not replaced. So that right there is the kicker, because that means the second time we take a card, there's going to be 1 less than there was to begin with. It says, then a second card is drawn at random. Find the probability of drawing 2 even numbers. Well, the first time we draw, we know there's 1, 2, 3, 4, 5 different outcomes. And we're focusing on even, so there's 2 of the 5 that are even. There's a 2 in 5 chance that the first time we're going to choose an even number. Now the second time, well, now we'll use multiplication. Remember, we're focusing on an even number. So let's just say that the first time we chose 6. So I'm going to cross it off the list. Okay, it had to be 6 or 8 because there were only 2 evens. So now we want to know the probability of choosing an even number again the second time. Well, now, because we didn't replace the card, there are only 4 cards left in the stack. There were 2 evens to begin with, but because one of those we're assuming was drawn the first time, there's only 1 of those left. So there's a 1 in 4 chance that on that second time, we would draw an even number. We can cross cancel 2 and 4 by 2. This just helps us get a simplified answer earlier, but I know a lot of you prefer to go ahead and just multiply it and then simplify at the end, and that's okay too. So ultimately, we have a 1 in 10 chance, which would be the same as a 10% chance of drawing 2 even numbers. Okay, moving on to page 779. Okay, at the top it says a number cube is rolled and a marble is selected at random from the bag at the right. Find each probability, show your work. These are independent events because what happens when we roll the number cube and what happens when we draw a marble has nothing to do with each other. Okay, so if we go ahead and start, the probability of rolling a 1 is a 1 in 6 chance. There are 8 marbles in this bag, 2 of them are red, so there is a 2 in 8 chance of us choosing a red marble randomly from the bag. We can multiply those 2 different probabilities. I'm going to cross cancel 2 and 6 by 2. 2 goes into 2 once and it goes into 6 3 times. And that's going to give me a 1 in 24 chance of those 2 events happening at the same time. Number 2, we want to find the probability of rolling a 3 and choosing a purple marble from the bag. So the probability of rolling a 3 is again going to be a 1 in 6 chance. There's only 1 purple marble in the bag, so that's going to be a 1 in 8 chance. So that's going to be a 1 in 48 chance of those 2 events happening together. Again, I'm not taking the time to convert these into percentages today. We know that we could use division by dividing the numerator by the denominator and then shifting our decimal 2 places to the right if we wanted to show this as a percentage. Number 3, the probability of rolling an even number and then choosing a yellow marble. Well, on the number cube, there are 3 even numbers, 2, 4, and 6. So there's a 3 in 6 chance, which of course is the same as a half if you wanted to start with that. And then there are 2 out of 8, or 1/4 of the marbles that are yellow. Again, I'm going to cross cancel by 2 here just to help me get closer to having a simplified answer. 3 times 1 is 3. 3 times 8 is 24. And I get a 3 in 24 chance. However, I know that both 3 and 24 have a common factor of 3. So I can simplify this fraction even further by dividing both 3 and 24 by 3. And when I do, I'm going to get a 1 in 8 chance of those 2 events happening together. Number 4. The probability of tossing an odd number on the number cube and then not getting green. So if I toss my number cube, I know that 3 of the 6 sides are odd, 1, 3, and 5. There are 8 marbles in this bag. 2 of them are green, which means 6 of the 8 are not green. I can cross cancel the 6's, and 6 goes into 6 one time. And that gives me a 3 in 8 chance of those 2 events happening. Now these again were all examples of independent events because one event had nothing to do with the results of the other. Number 5, A carnival game wheel has 12 sections. One of the sections contains a star. To win a prize, players must land on the section with the star on 2 consecutive spins. What is the probability of a player winning? So they have to spin that spinner twice, and both times they have to land on the star. So let's take the first spin. The first time they spin, we know there's 12 different sections and only one of them is a star. So there's a 1 in 12 chance that they're going to land on the star the first time. When they spin that spinner the second time, nothing is going to have changed based off the result of the first time. So there's still going to be a 1 in 12 chance of them getting the star. We can multiply those two probabilities together and we get a 1 in 144 chance of spinning that twice. That is why my kids never get to play those games at the carnival or the fair or the peanut festival, because the odds are not in their favor. All right, number 6. It says a standard set of dominoes contains 28 tiles, with each tile having 2 sides of dots from 0 to 6. Of these tiles, 7 have the same number of dots on each side. If 4 players each randomly choose a tile without replacement, what is the probability that each chooses a tile with the same number of dots on each side? Now let me help you make sense of this problem. We know that in a set of dominoes, there's 28 tiles. But out of those 28, 7 of them have double zeros, double ones, double twos, threes, 4s, 5s, 6s, okay, so on and so forth, okay? 7 of them have the same number on each side of the domino. Like here's the double 6, okay? So 7 of those 28 have the same number on each side. We got 4 players, and they are going to randomly just reach in, let's just say a bag of dominoes. You can't see what's in there. There's 28 in the set. They're going to randomly reach in there and choose a domino. And we want to know what is the probability that all 4 of those players would choose a domino that has the same number on each side, like the double 6, okay? So here's what we have to do. We have to start by saying, okay, the first player reaches in, and when he or she does, we know that as of right now, there's 28 tiles in that bag, and 7 of them have the double sides. So that first player has a 7 in 28 chance of choosing a double-sided domino, okay? But now when the second player reaches in there, because it said the first one did not replace it, we're not replacing them when we choose. Now, instead of 28 dominoes, there's only going to be 27. And because we're focusing on the chances of getting a double-sided domino, instead of there being 7 of those left, now there would only be 6. Now you got the third player. Because the first 2 have already taken out their dominoes and not replaced them, there's only going to be 26 left now. And now instead of 7, there's only going to be 5 left with double sides. Then the fourth and final player, they only have 25 dominoes to choose from, and there would be 4 left that had a double side to them, okay? So this is one of those where we would want to take our calculators because the numbers are going to be pretty large. So we're going to multiply all of our numerators here. So we've got 7 times 6 times 5 times 4, and we get 840. I'm just going to write it right here. And then we're going to multiply our denominators, 28 times 27 times 26 times 25. And we get 491,400. Now, because I love y'all and the weather's too pretty today to sit in here and divide this thing by 2s over and over again, and because I also have access to the answer key, I'm going to help you out right here. And I'm going to tell you that this really large fraction can be simplified by 840. If you divide 840 by 840, you're going to get 1. And if you divide 491,400 by 840, you're going to get 585. So there is a 1 in 585 chance, okay? That's not even a 1% chance that 4 different players could reach into that domino bag and choose a double-sided domino, okay? Very, very, very small chance of that. All right, last 4. By the way, number 6 would be an example of a dependent events because the outcome of one event does directly affect the probability of the next one. All right, last 4 here. It says Mrs. Ameldo's class has 5 students with blue eyes, 7 with brown eyes, 4 with hazel eyes, and 4 with green eyes. 2 students are selected at random. Find each probability, okay? So for number 7, we're going to find the probability of randomly selecting a green-eyed student, then a brown-eyed student, okay? So first of all, we need to know how many students are in her class. We've got 5, 7, 4, and 4. That's a total of 20 students altogether if you add those up. So when we start with the probability of getting a green-eyed student, we know there are 20 students there, okay? Now, it says that 4 of them have green eyes. So there's a 4 in 20 chance that that would happen. Now, once we have chosen the green-eyed student, that student is no longer in the mix. So now when we choose the second student, there's only going to be 19 left, okay? Now, out of those 19 kids, we see that 7 of them have brown eyes because we have not chosen a brown-eyed kid yet, okay? So now we can multiply. 4 times 7 is 28. 20 times 19, we'll pull our calculators out here again, gives us 380. I know I can divide both of these by 2 just to simplify it. That's going to give me 14 over 190. And because these are both still even numbers, I can divide them by 2 again. Just keep chopping away at it. And we're going to get a 7 in 95 chance of randomly choosing a green-eyed student and then a brown. I know that I can't simplify this any further because 7's a prime number and 95 is not divisible by 7. All right, let's look at the next one. What is the probability of choosing 2 blue-eyed students? Well, the first time that we choose a student, there will be 20. And of those 20, 5 of them have blue eyes. But once we have set aside or had that blue-eyed student kind of pulled from the mix, the next time there would only be 19 students left. And because we have already chosen one of the 5 with blue eyes, that means there would only be 4 blue-eyed kids left. So we would have a 5 in 20 chance the first time and then a 4 in 19 chance the second time. I can cross cancel 4 in 20 by 4. And that leaves me with, probably should know what 19 times 5 is right off the bat, 95. And then we can simplify both of those by dividing by 5. I don't know why we have that terrible shadow today there. And we get a 1 in 19 chance of choosing randomly 2 blue-eyed students. Okay? Last 2. What is the probability of choosing a student with hazel eyes and then blue? So again, 20 students to begin with. We have 4 with hazel eyes, so a 4 in 20 chance of getting a kid with hazel eyes. The second time, there's only going to be 19 kids left to choose from. Of those 19, we know that 5 of them have blue eyes. I can cross cancel 5 and 20 by 5. And that's going to leave me with a 4 in 76 chance of getting a student with hazel eyes and then blue. Now, both of these can be divided by 2. And 76 divided by 2 is 38. So we can actually go one more time here. And I know 2 goes into 38 19 times. So we actually have the same. If I would have paid much attention, I'd have realized this was actually the same 2 probabilities as number 8. And we would have known immediately that it was going to be a 1 in 19 chance as well. All right, last one, number 10. What is the probability of choosing a student with brown eyes and then blue? Still have those 20 kids. We have 7 of them with brown eyes. We're going to multiply that by the probability of then choosing a blue-eyed student the second time around. So now there's only 19 kids left. Of those 19, 7 of them have blue eyes. And then we can we can't do any cross canceling here. Wait, I messed up. 5 of them have blue eyes, not 7. I was looking at the brown. So 7 in 20 chance of a brown-eyed student, and then a 5 in 19 chance at second time of getting a blue-eyed student. We can cross cancel these by 5. And that's going to leave me 19 times 4. It's going to give me 76. I'm going to have to figure out what that shadow is. I think it's just how my phone is sitting up there. There we go. A 7 in 76 chance. And I know that 7 times 11 is 77, so I know it will not evenly go into 76. It's prime, so that's my only option. So a 7 in 76 chance. Okay? So just again, to reiterate, we can find the probability of compound events by multiplying the probability of one times the probability of another of the second event, but always be mindful, because if it is a dependent event, then the second outcome will depend on the outcome of the first event. Keep that in mind. I am going to work page 781, extra practice, and I will post a picture of the answer key if you guys want to challenge yourself to this page to make sure that you've got the idea. I'll put that out with the assignments for this week. All right, see you guys soon. Bye.